All right, good evening. My name is Paul Shand. I'm the head of the physics department here at UNI, and welcome to the 2026 Begeman Lecture. This lecture series is made possible by the generosity of the Jordan family. Richard Jordan and Frances Jordan are the grandchildren of Louis Begeman, the first head of the physics department when UNI was Iowa State Normal School. Begeman, under the supervision of Nobel Prize winner Robert Millikan, carried out the first accurate measurement of the charge of the electron using water droplets. Richard, who celebrates his 96th birthday this month, is unable to make it to the lecture this year. Still, let us applaud Richard for the tremendously positive influence he has had on the UNI physics department. The 2026 Begeman Lecturer is Dr. Peter Baruzzi. Peter's dad, Dr. Fred Baruzzi, was head of the UNI physics department from 1992 to 2001. While Peter was in high school in Cedar Falls, he took pretty much all the undergraduate physics courses we offered here in the physics department. He took a fair number of undergraduate math courses as well. Because he was so well prepared, he breezed through Harvard University, from which he received a bachelor's degree in physics and mathematics. He went to Stanford for his graduate studies and in due course received a PhD in physics. Peter remained at Stanford for a postdoctoral fellowship, after which he held two prestigious fellowships, a Giacconi Fellowship at the Space Telescope Science Institute, and then a Hubble Fellowship at Berkeley. Peter subsequently took an assistant professor of astronomy position at the University of Arizona. He is currently an associate professor of astronomy at Arizona. LinkedIn says, quote, Dr. Baruzzi researches how galaxies form, as well as links between galaxies, dark matter, and black holes, which I'm sure took some effort on his part to dumb down. Peter has published numerous papers in top journals in these areas. His dad sent me one of these papers years ago. I've now finished reading the abstract, and I'll read the rest of it when I retire. That should keep me busy for a while. The title of the 2026 Begeman Lecture is Reconstructing the Cosmos to Understand Our Origins. Please join me in welcoming Dr. Peter Baruzzi back to UNI.
You know, it's so nice to be back here. And Dr. Shand was just introducing me, but I feel like it's such an honor to be back because Dr. Shand was the first college physics professor whose class I took. And so he taught me all sort of 2 years of introductory physics that many of the students in this audience have also received. And so none of this would have been possible had I not started out with Dr. Shand, so thank you for that. But let me get to the topic of the lecture today, which is understanding our origins in the cosmos. And before I talk about the science, what I've been doing, let me just spend a few moments saying, why even bother study astronomy? And at least some of you in the audience, I know at least one person in the audience got dragged along here because her son is here. So my mom is sitting back there. And so I wanted to say, why is astronomy important to humans? And for me, there are two reasons. One reason is we here on Earth didn't pop out of nowhere. We are in the solar system, we're in the Milky Way galaxy, we're in this universe. And so as humans, we are just curious about why is it that we are here today? What are the conditions? What is our history? And understanding the universe is part of that history. And the other reason is that the universe is full of crazy things that we would have never imagined existed had we not seen them. Things like neutron stars and black holes and dark matter and dark energy, these are things that go beyond what we would have thought possible with physics. But understanding the physics of the universe also helps us understand the physics here at home, because they're one and the same. At least that's what we think. The physics out there that describes all these crazy things that we see also matters to us here. So with that, I'll start today's lecture and talk about a quest. Understanding Our Origins in the Cosmos is the title, but the quest for me is to make a movie of our own galaxy, the Milky Way galaxy, and make it as realistic as possible to describe all the physics that is happening that made us our home here today. So let me start out. Humans have been looking at the night sky ever since we were human. That's human nature. And over the past sort of 50,000 years, we've been building better and better instruments with which to see the night sky. And they've shown us more and more amazing things. So this picture here, I was actually asked by Paul, is this a real thing, or was it generated? No, this is real. This is the Hubble Space Telescope taking an image of the center of a cluster of galaxies. And what's being shown here is just the enormous number of galaxies all clustered together in the same place in this beautiful thing. And so instruments like Hubble, as well as the James Webb Space Telescope, have given us images, amazing images of galaxies. But what none of these images can do is show us what happened over time. And so, for example, in this image, we expect that many galaxies are so close together that they will crash into each other at some point in the near future. And we can find, because we can take pictures of so many galaxies, we can find galaxies that are literally this moment in the process of crashing into each other. And we can find galaxies that have crashed into each other and left all the remnants, all the tidal streams, all these shells, these beautiful streams in the sky to let us know that a merger has happened. But we can never watch a galaxy go through this. And that is because a human lifetime, or even the lifetime with which we've had pictures of the sky, the past 150 years, is nothing in comparison to the lifetime of a galaxy or the universe. And so the universe has been around for 13-some billion years, and we like to make a movie of how things have evolved over that time so we can learn about the physics of what goes on inside a galaxy. But we are stuck with just a very, very tiny percentage of that history that we can see. That's not to say that we don't learn really cool things from observations. So if I take this image of a galaxy cluster that I showed you earlier, there's more here than meets the eye. So this image was taken with the Hubble Space Telescope and shows you the optical, so what you could see with your eye, more or less. If you were able to see X-rays, you would see a different picture, which is this one. What X-rays tell us is where is all the hydrogen and helium gas around this space. So if you go to a dentist's office and you get an X-ray, the way that they make X-rays in the dentist's office is they accelerate and decelerate electrons. So they basically move them fast and then slow them down very quickly. And out in space, the gas is doing exactly the same thing. So in a cluster of galaxies, the gas gets very hot, and very hot means all the atoms are jiggling around very quickly. And in particular, the electrons are moving very fast and then colliding and then moving in a different direction and producing all kinds of X-rays. And so you see in this picture, not what the stars are doing, which is what Hubble will tell you, but what most of the matter is doing. And most of the matter in the universe, most of the ordinary matter, is in hydrogen and helium gas that was made during the Big Bang. Okay, so we see a completely different picture. Where are the galaxies getting their gas? And gas is important because gas is what galaxies turn into stars, which is why we can see them and why we live next to a star here today. The other very cool thing we can see with telescopes is we can see where gravity is. And this is very, very fun, because normally when I say, well, I can see gravity, people look at me a little bit strangely. But gravity bends the path of light. And because gravity bends the path of light, it acts a little bit like a lens. And so in this next picture here, taken by one of my former students with the James Webb Space Telescope, you can see streaks like this, these red streaks. And what's going on in this picture? In this image is a cluster of galaxies, and the gravitational pull from that cluster is so strong that light traveling near that galaxy cluster is being bent towards the Earth. And so you can think of all of this in very complex equations, or you can think of it very simply that gravity is acting as a lens, and lenses bend light. And just as lenses bend light, they distort the images of galaxies behind the cluster here. And so what all these streaks are distorted images of galaxies that are far behind this cluster here. And you can use the amount of distortion of those galaxies as a way of measuring how strong is the gravity from this cluster here. Okay? So you can use the shapes of background galaxies as a way to say how strong is the gravity in a given region. Okay, so you can learn all kinds of fun things by looking at the sky, by looking at these images. You just can't watch them move. Okay. So then, what can you do? Well, so I do not observations, but I do theory and simulations. And so the very simplest simulations that you can do are the simulations that include only one force, gravity only. And gravity is the force that's important for most large scales of the universe. And what do I mean by that? If you're far away from the galaxy that you're in, how does matter move around the universe? Well, it doesn't feel much of anything from light, that's the electromagnetic force, or from the weak force or the strong nuclear force. It mostly just feels gravity. And so if you have a bunch of matter and you turn on gravity, what will happen is matter that is in denser regions will pull other matter from its surroundings and grow into a bigger and bigger clump of matter over time. And that's what's being shown in this movie here. This is a so-called gravity-only simulation where you put all the matter in the universe approximately in the right initial conditions, and you press go, and then over time, you see things collapse into bigger, bigger structures, and then other sort of smaller collapsed objects orbiting around those bigger things. And so this would correspond to the matter underneath one of those galaxy clusters. You have a big lump here, and then lots of tiny little lumps around, which all host little galaxies. So you have a big galaxy in the center, and then hundreds of smaller galaxies, or thousands of smaller galaxies floating around in space. Okay. But matter is not the same thing as light. Matter is not the same thing as galaxies. Matter is not the same thing as understanding physics. And so the next group of folks to come along thought, well, we can do better than gravity. We can add other interesting things that happen inside galaxies. And it turns out there are a lot of interesting things. The folks who made this unfortunately decided it was a good idea to rotate through space as they were evolving this along, so please ignore that. What's being shown here is, in blue, the same thing as was being shown before, just where is most of the matter in the universe and how is it moving over time. But now the colors change, and what you can see is the temperature of the hydrogen and helium gas around galaxies. And you see these explosions happening everywhere. What's going on? Sometimes when a star is formed, it lasts for a long time, and thankfully that's happened with the sun. Sometimes when a star is formed, it lasts for a short time and then goes boom in a supernova. And another thing which causes explosions is black holes at the centers of galaxies, because as you add material to a black hole, some of it goes into the black hole and disappears, but some of it is heated and sent out in giant jets around the black hole. And so you see this beautiful fireworks of explosions happening in galaxies across the universe thanks to stars being formed over time. And then the movie shifts to something fun, which is the distribution of heavy elements. So elements heavier than helium and hydrogen, which all of us are made out of. And so these explosions, which launch out temperature and energy, also launch out the building blocks for life and distribute them all over the universe. So to understand our own origins, you also need to understand all these things besides gravity that go on inside galaxies. Okay. So now that I showed you this cool movie, it must be right because it's so cool, right? So it turns out that if you were to get 5 of the leading group's simulations and start them all with the same initial conditions, then, that is, feed them all the same numbers at the beginning, then you would get 5 completely different answers for how the universe should evolve. Okay, so what that tells you is, as cool as the movie I just showed you was, it's complete garbage. There's absolutely nothing right about it. Okay, and let me see if I can explain why is it that it's so hard to build a simulation of even a single galaxy. Okay. There is so much that happens, and that's part of why I'm attracted to this subject, is I love studying new things, and basically anything that you learn about in the subject of physics happens inside a galaxy. Okay, so what do you need? What are the ingredients you need to run a simulation of the Milky Way? Well, you need to know what happens inside stars, because some stars explode, some stars don't, and you need to know which ones do. So that means, and okay, my pointer's dying, so that's fine. I'll just leave it here and point. So some stars will explode, some stars won't. The scale of a star in sort of units that we might talk about is about 2 light seconds. So light, if it was uninterrupted, would travel from the center of a star to its edge in about 2 seconds. Okay. But stars don't just form out of nowhere. Stars form in protostellar disks, which are on scales of about a few light months. So light would take a few months to travel to the edge of the disk in which stars form. Stars form often in binary configurations, so you have to know the surroundings around the star to know the context in which the star was created, to know how it will evolve. But protostellar disks don't just show up in the middle of a vacuum. They show up in what I call giant molecular clouds, sort of regions of hydrogen that are so dense that instead of atoms of hydrogen, they combine into molecules of hydrogen. And these are on scales of sort of a few light years now to hundreds of light years. And giant molecular clouds don't show up in the middle of nowhere either. You have many, many tens of thousands of them present in galaxies like our own galaxy, the Milky Way. And again, the conditions, the magnetic fields and so on that determine how a molecular cloud fragments into protostellar disks are determined by the galaxy in which it finds itself. And galaxies now are talking about scales of tens of thousands to hundreds of thousands of light years. And of course, one galaxy by itself can have an explosion, a supernova, that sends material out that changes the cooling rates in the gas in galaxies around it. So it's not just one galaxy that you have to simulate, but you have to simulate all the galaxy's neighbors, too, to understand how the galaxies impact each other's formation. And in fact, there are some things, like the ionization state of the gas, that aren't just affected only by nearby galaxies, but by galaxies across the observable universe. And groups of galaxies might be on scales of millions of light years. The observable universe is now scales of tens of billions of light years. And so the end of this is that to simulate an entire galaxy, you have to simulate scales from the insides of stars, light seconds, all the way to the entire observable universe. Okay, so let me try to put this in more human terms. Let's say you're a sociologist and you want to study human behavior. Trying to simulate like this is saying, let's simulate the human behavior of everyone in Cedar Falls down to the atoms in their bodies. That is the scale of this problem. And this is not a problem that will be solved in 10 years or in 50 years or 100 years. This is just impossible. Okay. And so the situation when I started my PhD 20 years ago is that everyone was sort of trying to add different things to their simulations to say, maybe we can make better galaxies by doing this or that. And I was very, very lucky to study with someone who realized that this was all going to go nowhere. Okay. So what can we do? A lot of science is about starting from something that we do understand and going to something that we do not. So using what we do know as a bridge to get us somewhere that we don't. And gravity is something that we understand. So if you ask 5 different groups with the same initial conditions to run a gravity-only simulation, they would get the same answer to within a fraction of a %. Now, we would like to take that information and use it to understand what are the galaxies that grow in different regions of matter. Okay. And the way of doing this for the past sort of 50,000 years was to think very hard about it and come up with a good explanation and then show that it was true. And this hasn't worked for this problem. So we need to try something else. And so the something else that I started out trying was, oh, thank you. Great. Oops. Oops. There we go. Okay, good. So the way that I tried to do it instead was to use a computer to figure out how to get the right galaxies into the right places in space. And the sense is that if you have to think about it, the physics that you can learn is limited by human imagination. But if you ask a computer to do it in the right way, then the physics you can learn is limited only by the information that the universe can give you. And we're lucky that we live in a big universe with lots of information, and so it tells us information about millions and millions of galaxies. And so that makes this approach possible to learn something about the physics by asking the universe how it does what it does. Okay, so let's see if I can, again, make some analogies to what we know as humans here on Earth to describe a little bit about how this process works. So the general approach is I would take an image of galaxies and break it up into pieces of individual galaxies so you can see some cutouts like this. And then I go to a simulation that I know is roughly accurate about where matter is in the universe. And then I try a guess for putting galaxies into the right places in the simulation. Okay. Why is this a good idea? Well, the first thing that will happen is I'll put galaxies in totally the wrong place. And so how do I fix that? How do I even know that I put things in the right places versus the wrong places? It turns out there's a lot of information about which galaxies, there's a lot of information in the knowledge of which galaxies are neighbors or close to other galaxies. And so I've just drawn some connections between galaxies like this. And you can ask, are the galaxies in the right configuration or are they not? Okay. So I'd like to do an interactive exercise because that's a fun thing to do with an audience. I'd like you to look at the next image, and the next two images will show some animals. And I want you to raise your right hand if you think that it's something that you would see in nature. And I want you to raise your left hand if you think that it's not, that it's somehow artificial in some way, that it's not the right description of how animals behave on Earth. Okay, so here we go. 1, 2, 3. Here's the first one. Okay. So artificial. This one is definitely artificial. I pasted a cat on this image. Okay, let's do one more. So next one, 1, 2, 3. That. Natural or artificial. Okay. So I see some raising the left hand and some raising the right. Okay, good. So there's some disagreement. This is obviously happening in a zoo instead of in the wild. So yes, it is real animals, but no, it is not representative of nature. But with this exercise, you can see from your own experiences that neighbors actually tell you a lot about whether something is realistic or not. And so even though you may not be able to look at this image and say, gosh, these galaxies are totally in the wrong places, a computer can look at this and compare the locations and connections between galaxies and say, well, these actually don't look right, and we need to shuffle these around enough times until we come up with something that looks statistically indistinguishable from what the real universe looks like. And if you have enough galaxies in the real universe, that narrows down the number of solutions dramatically. And so you only get one or a handful, small handful of solutions for how galaxies can be put into the distribution of matter so that they are looking like what the real universe looks like. Okay, and so I'll just play a movie of what one of these realizations of the universe looks like. So every galaxy here is in statistically the right place. So if you were to look at somehow the statistics of this universe, where the galaxy is distributed, how are they clumped together, are there lots of galaxies in one place or not? All of that would match exactly with the real universe. And since it's a fake universe, I can fly through it at a quadrillion times the speed of light and show you this movie. But let's go back to the original plan. Since there are physics students in the audience, I did want to include one technical slide to explain what is it that I'm actually doing. So I start with a gravity-only simulation that I mentioned before. And what I want to know is how galaxies depend on that underlying distribution. And this function here is effectively a machine learning or a neural network or an approximation for what the underlying true relationship between matter and galaxies is. Any guess for what this is? Then I can apply to the simulation and generate a simulated universe. And then I can ask, does that simulated universe look like the real thing? And if it doesn't, which it probably doesn't at first, then I can use an algorithm to try again millions and millions of times until I get a universe that does look like the real thing. And that also helps me solve for what is this underlying connection. And that's almost magical because I can solve for that underlying connection without ever having to measure the details of the matter distribution, as long as I have enough observations of galaxies in the real universe to use this information coming from the neighbors. Okay. So that's the one technical slide, and we can go back then to things that everyone can understand. So what are applications of this? One application is to the original question of building a movie. And so we know how gravity moves matter around. And so can we use that to somehow say how galaxies grow over time? And it turns out the answer is yes. Okay, so let me see if I can explain a little bit how this works. If there's a galaxy close by, let's say a galaxy where Paul is right now, if there's a galaxy close by, the light that is just reaching me now from that galaxy has traveled a short distance, and so I'm seeing that galaxy roughly as it is at this moment. Now let's say there's a straggler who's coming in right now from those doors back there. Light from that person is now reaching me after traveling a longer distance. And so that meant that light needed to travel a longer time from that person back there to me. And so instead of seeing that person as they are right this moment, I am seeing them as they were a few nanoseconds ago. Now we multiply this by a billion billions, and the same thing happens for galaxies in space. A galaxy that is a million light years away, I am seeing as it was a million years ago. A galaxy that is tens of billions of light years away, I am seeing as it was potentially billions or tens of billions of years. Well, not tens of billions, but over 10 billion years ago. And so I can see galaxies at all different ages of the universe just by looking for more and more distant ones. And if I know how those galaxies map in to the matter distribution, then I can build a movie of how a real galaxy might have evolved. And so this is showing successive images of galaxies observed at earlier and earlier points in the history of the universe that would grow into a Milky Way-like galaxy today. All right? So there's a statistically reasonable history of the Milky Way shown here as it was 3 billion years ago to 9 billion years ago, all the way back to over 11 billion years ago. And I can do that reconstruction because we can see galaxies at all different points in the history of the universe. Now, how did I solve the problem of having to simulate stars all the way to the entire observable universe? Well, luckily, the observable universe already did that for me. So it already is the perfect simulation of everything because all the physics is included, even the physics that we don't know about yet. And so I can use the real galaxies and connect them to the simulation, what we think we understand, to reconstruct then how real galaxies evolved. Okay, but we're not quite done yet. This movie is a movie of how a galaxy like the Milky Way might have evolved. And if you've ever taken a writing class, you know that you should not use qualifiers. And so what we'd like to do in the future, and I'll talk a little bit about this at the end, is make not just a movie like what the Milky Way would have done, but a movie of what the Milky Way actually did. Okay, so before I get there, I want to say a little bit about some applications of this in terms of the physics that we learn, because this is a physics lecture. So one thing that we learn is why certain types of galaxies are better at turning hydrogen, helium gas into stars than others. And we can come up with hypotheses, testable hypotheses, and say, oh yes, some galaxies, like our own galaxy, sit in a sort of well of gravity that's strong enough to prevent gas from leaving the galaxy very far when stars explode. And then that gas can sort of rain back down and form more stars. Whereas the smaller galaxies, the gas escapes too easily. There's not enough gravity around to keep that gas around, so it just goes boom when a supernova goes off and never comes back. Or if the gravity is too strong, then the gas gets too hot and it's hard for it to cool. So we can learn some physics by looking at where galaxies form stars more efficiently. And tying this back into home, we can also say, for example, when and where has the universe been forming all the Earth-like planets? And so we can ask, how late are we, or how typical of a galaxy are we on Earth? And so just very briefly, what's being shown here is this is about the size of the Milky Way galaxy. And so most of the Earth-like planets, shown in yellow here, have been forming in Milky Way galaxies because those are the galaxies that are most efficient at forming stars, which are then the most efficient at turning gas into planets, too. But then it turns out we're a little bit later. And so most of the stars, most of the Earth-like planets, both in the Milky Way as well as the rest of the universe, were formed before the Earth. So that's sort of food for thought if you like thinking about extrasolar planets and any civilizations out there. Okay. So now let me say a few words about the future. So I mentioned we'd like to do better than just likely history, or almost like what the Milky Way would have done. And so one aspect of this is that we will get a lot more information. So this picture shows the Rubin telescope, which is now operational in Chile, and will take pictures of the entire sky every few nights. And so one aspect of that is we have a lot more information with which to calibrate out uncertainties. But then we also have fancy new tools. And so this image that I'll show you, which will turn into a movie, this image looks very unassuming. And if you were to look at it, it wouldn't look strange at all. But if you give it to a simulation, and you run it forward, then what happens, well, it doesn't look like a galaxy. But it does look suspiciously like a logo for a program. And so that's what's been done here, is that now what we have are differentiable simulations, and what that means in technical terms is you take a derivative of the final conditions with respect to the initial conditions. What it means in everyday language is you can create a simulation that ends up with whatever configuration of matter you want. And so instead of having a logo here, we could have the Milky Way here, and our neighboring galaxy Andromeda here, and the large and small imaginary clouds here and here, and all the other surrounding galaxies in the right place, as opposed to just making a universe that's statistically indistinguishable. We can make a universe that is exactly like the real thing. And so this requires a ridiculous amount of computing power, and is sort of just becoming possible. But this is what the future of the field will look like, is being able to say, for any galaxy, including our own galaxy, the Milky Way, what exactly was the history of that galaxy over time? And so there are a lot of fun things that happen in galaxies. I mentioned a few of them, like black holes and star formation, and there are lots of other fun things happening in there. And with these types of movies, instead of just seeing single images from observations, we'll be able to reconstruct how each of these things affected the galaxy our own galaxy, any galaxy, over its lifetime, and then be able to understand what are the important physical mechanisms that made us possible, as well as all the galaxies in the universe possible. Okay. Good, so I wanted to leave a lot of room for questions. I also, before we go to questions, wanted to thank some very special professors because, as Dr. Shan mentioned, I've been taking classes at UNI from a very long time ago. So I wanted to give a shout out to Dr. Shaw, who taught me calculus, Dr. Shand, already mentioned, Dr. Stanley, who taught me combinatorics, Professor Hagedal, who taught me how to play the violin, as well as my dad, who taught me how to be curious about the sciences. So I'll stop there, say thank you, and ask for questions on anything. I mean anything. So you can ask me about something I've talked about here, or you could ask me about planets or black holes or neutron stars or the University of Arizona or anything. So please.
Yeah, thank you very much for a nice talk. So you mentioned that there are 5 leading groups, and they basically did these 5 movies, and the movies are completely different.
Yeah.
What is the main reason for the difference? Or
Yep.
different parameters, or?
Okay. So it's clear that you can't simulate all the way down to stellar interiors if you're simulating a big chunk of the universe. And so what everyone does is they have a scale or a mass below which they can't resolve any physics. And at that point, which is called the subgrid scale, they have to guess what is the emergent physics that's responsible for all the effects. So things like exploding stars or growing black holes, what happens below the scales that you can resolve that will then propagate to all the scales that you can resolve. And so everyone has a different subgrid physics model. And what are some of the differences quantitatively? Well, people will put in different amounts of energy for supernovae. They'll put in different types of sort of how that energy affects the surroundings. So thermal feedback versus winds, for example. Or for black holes, it might be a lot of kinetic energy that comes out in jets versus thermal energy. And things like diffusion of metals, which affects cooling on small scales, but which is not well modeled by the types of resolutions that people are using. So there are a lot of things that happen on tiny scales that you would like to be able to model, but are impossible to model at the same time as simulating large regions of the universe.
I had a question. More into the model that you developed?
Yes. Great. Okay. So let's see if I can just, there's my son. Right. So I gave a pretty schematic overview here. What's being modeled? It's the galaxy. What does the galaxy mean? So it means the mass of the galaxy, how much gas is around the galaxy, how big of a black hole is inside the galaxy, how much dust is affecting the colors, because dust, just like on Earth, which changes the sunsets to be red, also changes the colors of galaxies to be red. And so, right, so what's happening, or what's happening? So what we're doing is modeling the growth of the black hole, the color of the galaxy, how many heavy elements are being produced by the galaxy. Do they stick around? Do they not stick around? How much gas in atomic and molecular hydrogen is around, and how many stars has the galaxy been formed? And we can keep track of all of that as a function of the surrounding matter density. And the technical term for that is the dark matter halo mass and the properties of that halo, including its spin or its growth rate and things like that. You can think of all of this as an empirical model. And what is an empirical model? It's a model that none of the physics are put in ahead of time. And so instead of, I think supermassive black holes grow in a certain way and eject energy in a certain way, and I need to move the gas around in a certain way to compensate for that. Instead, we model that there is a supermassive black hole, and it grows in some way that's related to the surrounding matter, but we don't say anything more than that. And we have a very flexible fitting function that describes how the galaxy grows, how things inside the galaxy grow as a function of the surrounding matter. And that's important because the universe has its own ideas about how to run galaxy formation that we just don't know about yet. And the only way we can learn new things is by having a very flexible model so that the universe can teach us how do galaxies have to grow to reproduce the observations that you see. And because we have so many observations, millions of galaxies now, and with the Rubin telescope, billions of galaxies, that limits the flexibility to only a solution space around the right answer. So that's why I said we're able to use the universe, the information from the universe, to teach us how galaxies must form to match all the observations simultaneously. Because to match one galaxy, well, you don't know if you really got everything right. But if you match a billion galaxies, then you're a little bit more sure. Great question.
Go with me. This might sound a little dumb. Okay, so you're using computer simulated models, which in my mind, I'm like, okay, you're getting all of the data that was collected by all of the humans, and I can see how the collective gives us more information. But we're also gathering data with machines that were made by humans, and so I'm like, what is the plan for overcoming the human factor here?
Great. I had a slide prepared. Let me see if I can describe the sociology of astronomy in one slide, which is you have people who focus on different areas of astronomy because each area is so rich that you can spend your entire lifetime just mired in that and nothing else. And so there are people who think all day long about cosmology, that is the initial conditions of the universe, how much matter there is, how much energy there is in the universe, how the universe size changes over time, cosmologists. And there are people who think all day about how galaxies form. There are people who think all day about how stars form and explode and do interesting things. And there are people who think all day about how to build instruments. And there are problems in each of these areas of science. And they are problems that affect all the other areas. But because there's so many problems already in each area, no one wants to talk to other areas to figure out how to solve all the problems at once. Let me give some examples of that. The people who study cosmology, who build big instruments to measure, say, lots of galaxies' positions in the sky and use that to say something about the expansion of the universe, those people are limited by uncertainties about how galaxies form. The people who study how galaxies form, like the formation of the Milky Way, are limited by our understanding of the initial conditions of the universe. But that's what the cosmologists study. And they're also limited by errors in how people interpret the light from stars. But that's what someone else studies, right? And each of these has uncertainties driven by other people. And so this has been going on for literally the history of astronomy. And I think it's possible to build a single machine that can interpret all of this at the same time. So in other words, you can write down what are all the problems in each field, like this. And each field depends on problems in other fields, but there's actually enough data available to calibrate everything all at once with joint uncertainties. And so what that means is you have a single computer, and computers don't care about how much information you put into them, so you're allowed to try to solve all the problems at once. And you can build something that models all the problems in the instrument. So for something like the Rubin telescope, which I now lost. There it is. There's a simulation program that literally models the path of every photon that comes in this thing and how it bounces around and scatters and interacts with bits of the telescope before it finally sort of goes down to the detector. And there's a separate program for how does the detector have all these challenges and issues with the CCDs that go in. So to the extent that we are able to model what we have, we can get around some of the human infallibilities. And then we always have to add in nuisance uncertainties for the unknown unknowns that we didn't know how to model with this telescope, because stuff is always different in real life, right? That's always something that can be checked. There are different ways of saying, okay, this doesn't match exactly, but I know that I can explain everything down to a certain precision, and so I'll accept that I don't know everything beyond that.
So there was a slide about dark energy with a
Yes.
triangle. I was also wondering on that. And then also, what is the purpose of using like the relative position of universes in your model?
Okay, so let me answer the first question about dark energy first, and then you should ask your second question again because I will have forgotten it. Okay, so what is happening? Here's the nutrition label for the universe. On the top, there's galaxies, so that's all the light pretty much that the universe produces is coming out of galaxies. And the actual contribution to the matter is around, well, under 1%. And then ordinary matter in the universe, which is mostly hydrogen, helium gas from the Big Bang, is about 5%. And then we have this stuff, this dark matter and this dark energy. So what is it and why is it there? Dark matter is there because we have too much gravitational pull in the universe to be explained by the matter that we can either see directly because it's emitting light, or infer that exists by other reasons. And so sometimes you can directly see this in X-rays. Sometimes you can see it because it absorbs light from background galaxies. But you can usually measure how much of it is there that interacts with light. And it's not enough to explain the forces that we see in the real universe, the forces that bend light, the forces that accelerate galaxies around galaxy clusters, the forces that cause the cosmic microwave background to have the wiggles and blobs that it does. And so we end up needing to add extra matter to explain that doesn't interact with light, and that's why we call it dark matter. Do we know what it is? Absolutely not. Have we tried for 50, 60 years? Yes, and still come up empty-handed. So we just have no idea what it could possibly be so far. We just know that it's very, very hard to explain everything we see unless we invoke some component of matter that doesn't interact with light. And dark energy is even more mysterious because, well, anything, matter, will accelerate in a certain way under the force of gravity. I have no idea what's in this laser pointer, but if I dropped it, I would be in trouble because it would fall to the ground and shatter, right? And in fact, I distinctly remember the first day of class with Dr. Shand, he took a piece of chalk and said, what happens if I drop this? And the entire class was skeptical, thinking like this is a magic trick. And he dropped it, and it fell on the floor exactly like you would expect gravity to do, right? So gravity doesn't care. It will cause things to slow down and to fall back down together. But the universe isn't doing that. Instead of the universe expansion slowing down, or at least slowing down to a steady rate, it's accelerating, so it's getting faster and faster. So galaxies that are distant from us are getting farther away from us faster and faster. And the only way we can explain that is to say that it's not all matter in the universe, but there's some other force that we're going to call dark energy because that will get the Department of Energy to give us money. We're going to say that that's what's causing the universe to get larger, faster, and faster. Okay, now you can ask your other question.
I was also wondering, what was the purpose of using the relative configuration of the universes?
So the relative configuration of galaxies. Great. The purpose of using the relative configuration of galaxies is to let us know if the universe looks the right way or if it doesn't, and how far away from the real thing we are. And so if I'm producing a universe that looks like this, I know I'm really far off. I know I'm producing a universe like this. I'm still far off, but not as bad. And so finally I get a universe that looks like the real thing, and that I can call my job is done.
I had another question,
Mhm.
kind of back to the machine learning model. Is there a reason why you don't include any like known physics knowledge into the model? Because that can help.
That's such a good question, and it's a question I'm asked all the time by people who run simulations, especially because they're like, well, we already know that there's stars, and the stars explode, and we already know that they're black holes, and the black holes send out energy, so why don't you use that? And the answer is really interesting because it's not that we wouldn't gain some sort of better knowledge from that information, right? So I could say there's something that we do know about how galaxies link to the matter distribution, and let's use that. But it turns out that it's not that much of a benefit. And it's not that much of a benefit because the amount of information that we have coming from the galaxies in the real universe is so overwhelming that it doesn't matter what else I put in as prior information. What comes out at the end of the day is so constrained that it just doesn't matter. So if I put in, okay, I think there's supernovae in low-mass galaxies that are causing them to be inefficient at forming stars, it gives me the same answer because it's what's required by all the information in the universe, and I haven't actually benefited from that. So it's not that that's not true, it's just that the universe has so much information already that we don't need to put in any prior information. It just comes out without us trying.
Yeah, so we talked earlier, and you said that you're using these computer facilities like tens of thousands of cores to run a calculation. So with all this fast development of quantum computers, do you think that this is something that may be useful for computational cosmology?
Right, so the question is about quantum computing, if it's useful for this kind of analysis. And answer so far is no. No one's thought of a good algorithm to use with quantum computers to accelerate this. What ends up having to happen is you need to use so much memory to generate this that it just overwhelms the current quantum computers because you can only store sort of a tiny fraction of things on quantum computers right now. Yeah, so the memory requirements just make it so difficult to fit that it's just faster to use normal computers and GPUs.
This is not a physics question, just a general education question. Think back 20 or 25 years ago when you learned a fact in a high school or college class that you knew absolutely was true, and now you know it's false, and then comment for the young people in the audience what that might mean for them teaching and learning science for the next 30 or 40 years.
Well, so I have to say thank you to one of my high school teachers. So what was something that I learned that turned out to be false? So rather than singling out Paul, there are a lot of things that I learned that didn't come from the class itself, but came from the community, came from the culture of the classrooms that I were in. And unlearning those things turned out to be very important for me personally and contributed to my growth as a teacher. So one thing that I learned, for example, I had always been taught that the person in the class who did the best was sort of morally the best person. And that was sort of what I absorbed from the culture of society. And not only the best person, the person with the brightest future. And now having been 20 years removed from those college classrooms, I can say emphatically that's not the case. And you could never have picked who would be the most successful just by their performance in the class. And in a similar vein, what were the classes that were the most valuable? There's sometimes a lot of emphasis placed on if a class is very rigorous, it must be very useful. And that's what you feel at the end of the class, is I worked really hard and I got a B in this class, and so this must be teaching me a lot. And I learned from my wife, who studies psychology, that this is something called cognitive dissonance, and actually has no bearing in whether you will use this material or learn it well. And there's a class I took in college that literally I had to spend 40 hours a week on the homework for this class, and I remember almost none of it. And I use almost none of it 20 years later. So there are a few hard lessons like that that I had to learn over the course of taking classes and now being in a position to teach classes. So thanks.
So Peter, from these simulations that you run, will you ever be able to infer anything about dark energy or dark matter?
Great. Yes. So once you're able to use all the information, then you're able to perform an equivalent analysis of any experiment that we have today. So there are certain experiments designed to, say, measure the expansion rate of the universe. If you use all the information, then there are theorems which basically guarantee that you will do as good or better than anything existing today that's specifically designed to measure that. Because if you use the same information that those instruments gather, you can only do better in your power to say how much dark energy is there, is it evolving, is its equation of state evolving over time? And for the Milky Way, for example, what is the dark matter distribution now, as well as any point in the history of the Milky Way galaxy?
Close are we to determining what they actually are?
It's really anyone's guess, because we've tried many different things. We've looked for weakly interacting particles. We've looked for compact objects like black holes, primordial black holes. We've looked for axions, particles that might interact in strong magnetic fields with light. We've looked for all kinds and all zoos of different things and turned up nothing. On the qualifying exam, and I have thoughts about qualifying exams, I once gave a problem that said, what if dark matter were just giraffes? How would you be able to know? And it turns out that you wouldn't be able to know, because giraffes, to first approximation, don't interact with light. So if you spread out giraffes across the universe for the right density to make them act like dark matter, they would be so far apart that you would, number one, not be able to see them. And number two, if you had a big cloud of giraffes over here and a big cloud of giraffes over here, they would be so far apart that if you tried to ram them together, they would just all pass through each other like a cloud of flies. So we really don't know what it is. We have some constraints in some areas that it cannot be this or cannot be that, but they are weak constraints. No. No. And it turns out it actually doesn't matter too much, because just as you showed us on the first day of class, if I drop this laser pointer, it'll accelerate in the same way as if I drop a bundle of dark matter. And it doesn't matter what's in that matter, it'll accelerate the same way, because gravity doesn't care what matter is. And so that's how we can run these simulations, even though we don't know what dark matter is, as long as we know how much of it is there and the fact that it doesn't interact with light, we get the same answer after running these simulations.
One last question from me. I would guess that the quality of your simulations depends on the quality of the actual astronomical data that you have.
Mm-hmm.
And the universe is so huge that we're only able to focus on some tremendously small fraction.
Yep.
off it using the Hubble telescope and James Webb.
Yeah.
So will the quality of your simulations be forever limited by the quality of the data that's accessible?
This is a wonderful question. So, for example, if I want to build a movie of the Milky Way, does it matter that James Webb can only give me sort of low resolution, by Milky Way standards, images of distant galaxies? And the answer, interestingly, is no. And the reason for that is that if you can tightly constrain how the galaxy maps onto the dark matter by adding little bits of information here and there from different galaxies, then the overall amount of information that you have is still overwhelming, and the constraints on what this looked like are very tight. And so even though I don't know a lot of information for each individual galaxy, then the combination of all that information still gives me very good constraints on how the Milky Way would have evolved at early times. And so then I can say, okay, now I can reconstruct the growth of the Milky Way because I know this function, this mapping between matter and galaxy extremely well.
So what we would do in condensed matter is, Pavel, Dr. Lukashev, would run his simulations and predict the properties of some material that we haven't seen yet. And so we would then run to the lab and make that and see whether or not it matches up with the simulations. Is that something that you intend to do? Meaning that you run a simulation on a part of the universe that we haven't looked at yet with the James Webb and see whether or not the James Webb actually captures it.
Great. This is a difficult question because of how the universe is made. And so you can ask, for example, if I run a simulation like this, how do I know that it's right when it matches no part of the universe? And the answer is, well, the statistics of this look correct given what we know of the universe. And so, no, you'll not ever be able to run a simulation that predicts a part of the universe that hasn't been seen and get it exactly right. But what we can do is say, let's predict the statistics of a region that we've never seen before, and that we should be able to get exactly right. So in other words, James Webb might observe now up to sort of galaxies a few 100 million years after the Big Bang. We can then predict, okay, how should the galaxies even earlier looked, and with a bigger, better telescope 20 years from now, then we can observe those galaxies and see, are they actually the right sizes and shapes and numbers? What we can't see is the information that's required to reconstruct the initial conditions for those galaxies, so we won't ever get the right things in the right spots, but we can at least get the numbers and the shapes and the sizes and colors right.
Any final questions for Peter? All right, if not, let's thank the speaker again. You're certainly welcome to come forward and ask Peter your individual question, for sure. Yeah, thank you, Peter. Get Pavel's pointer back to